Today we are going to start section 3.1, which is Numeration Systems. This is a very different chapter, and this section of the chapter in particular is also quite different even than the rest of what follows. The point of this chapter, as a general overarching why are we looking at it, is to give you some appreciation for the fact that you work within a number system that has developed over time. It didn't just come out of nowhere. People tried lots of things before we got the enumeration system that we actually have. So to start with, I'm going to talk about what our enumeration system is. Our enumeration system that you use every day is called the Hindu-Arabic numeration system. It was developed by the Hindus and transported to Europe by the Arabic. Facts that you know about your enumeration system, though you may not have ever thought about them quite this way, is that all numerals are constructed from 10 digits. Those digits are 0 up through 9. So 10 is a two-digit number, right? Your individual digits do not include the number 10. Place value is based on powers of 10, right? So we have the hundreds place because that's 10 squared. We have the millionths place because that's 10 to the power 6. All of our place values are powers of the number 10. And as a reminder, when we talk about exponents, like I just said, 10 to the 6th, we're talking about multiplying whatever the base is together that many times of the exponent. So a to the n is a times a times a times a, whatever, n times. Okay, so that's where we are today. And what we're going to do now is we're going to go in reverse thousands and thousands of years and look at some of the different things that have been done in history for numbers. And the first one we're going to look at is the Egyptians. The Egyptians have some interesting pictures. So I'm going to pause and just not talk for a minute or so while you draw these little guys down, and then we'll talk about what each of their value is worth.
Is this contemporary math stuff?
It is taught in contemporary math that you took with me online. It's
Yes.
not taught in the contemporary math that we teach in the classroom right now.
Okay.
Right now,
I
anyway.
remember a lot of
Mm-hmm.
it. Yeah, see.
Just do your best on the drawings. Okay, raise your hand if you're glad these are not the numerals you write with every day. Some of you are artists and you're like, no, this would be fantastic. I like this way. All right, so I'm showing you what our book uses as the visual for their numeral. There are some books that do them a little bit differently, little different resources. I'm going to guess that probably all the books are all correct and they were done differently, kind of like when you think about how do I write the letter A and how do you write the letter A. I'm going to think it's probably something kind of like that. So each of these has a value that corresponds to a numeral that we have. And all of the values are based on our powers of 10. So the vertical staff is worth 1. A heel bone is worth 10. A scroll is worth 100. You notice a pattern? Yeah, powers of 10, right? What is the lotus flower going to be worth, do you suppose? 1,000. How about our pointing finger? 10,000. Pollywog? 100,000. There are resources that I've used before that call the pollywog a burbo fish. It's another phrase that you'll hear used for that image. It's supposed to look like a fish. I mean, my picture's not great, but you can pretend. And I think the last one's an astonished man because he's worth $1 million. I mean, if I were worth $1 million, I'd be astonished. Pretty exciting stuff right there. Okay, and what they do in their system is if they want the number like 3,000, then they write the 1,000 symbol 3 times. And that's all it is. So when you're taking a look at their numerals, you can actually move in and out of our numeration system pretty easily. But before we do that, what we're going to look at in each of the numeration systems that we encounter is how we go about finding the number that comes before this number that we're talking about, and how we go about looking and finding the number that comes after. So let's take an example. You have 3 scrolls and a heel. And we're going to actually jump to the number that comes after. So we're going to do part B before we do part A, because it's easier. In order to get the number that comes after this, all we would need to do is add 1 to it, right? How do I get the number that comes after 437? Well, I add 1 to 437 and I get 438, right? For example. So I just need to add 1 to it, and adding 1 to it means adding a vertical staff. So I can do that. So over here, the number that comes after this would have my 3 scrolls and the heel bone and a vertical staff. That's the number that becomes after our number. In general, to take the number that comes before, we would just need to take a vertical staff away. What's the problem here?
It's to 10.
Yeah, there is no vertical staff written in the number that I currently have, right? So it's kind of like you have a $10 bill and somebody says, give me $1. Well, you can't really do that, right? You have to change the $10 bill into 10 ones, and then you can give them the $1 bill, yes? Mm-hmm. Same idea. So we're going to take this vertical staff and we're going to remember, like you said, that it's worth 10. Okay, I said vertical staff, it's a heel bone. I'm sorry. We're going to take this heel bone. We're going to remember that a heel bone's worth 10. And so if I take the heel bone and I turn it into 10 vertical staffs and I take a vertical staff away, that's going to give me, 9 vertical staffs that would have come before the heel bone, and the scrolls at the beginning are the same. The scrolls are terrible today. So you end up with 3 scrolls and then 9 vertical staffs. And the question asks, what is this value? And it means the original value that we were given. So what is this value in our system? So what is it?
310.
310.
No, it's 3010. Sorry.
Oh, is it scroll thousands? No, scrolls hundreds. You're right.
Is it?
It is. Scrolls are hundreds, heel bones tens, so 310. Okay, everybody good with that? Okay, so we're going to go the other direction now. We're going to take one of our numbers and we're going to write it into their symbols. The number we're going to do is 23,145. So we're going to start with the 2 at the beginning. The 2 is in the thousands place. So how many thousands do I have? 2. And what's the thousand symbol?
It would be the pointing finger, yeah. Because it's 23.
Oh, 10,000 is what I meant to say.
Yeah.
To have 2 10,000s. What's my symbol for the 10,000?
Pointing finger.
The pointing finger. Good. So I need 2 pointing fingers. Something like that. I don't draw any better than some of you do. I guarantee it. How about the 3? 3 lotus flowers. Oh, that was just 2. I almost stopped too soon. There's my 3. How about the 1? 1 scroll. The 4. 4 heels, 4 heel bones. And the 5?
Staffs.
Staffs, right. 5 staffs.
Okay, well.
Okay, so somebody tell me something that you think is good about this system.
It's very pleasing to the eye.
It looks pretty. Okay, Valerie thinks it looks pretty. I'm not sure my picture looks very pretty. It holds a zeros place. So if there's a 0, I know it, right? So if there were a 0 in my number, I just wouldn't have any of that picture. That's a good thing, for sure. I think it's pretty easy for us to convert in and out of it for our system. What's something that's maybe not so friendly about this system? It's time consuming, definitely.
It can get confusing if you don't know them.
Okay, so
Like, memorize them.
if you don't draw well, or if you don't remember the symbols very well, I don't know that if you were Egyptian that you would have that concern. You'd probably remember the symbols okay. But it'd be time consuming whether you knew the symbols or not, right? I mean, what if your number that you had to write down was 99,999?
Oh.
That'd be a lot of symbols, wouldn't it? You'd be drawing for a long time. Yeah, so there's some some pros and some cons to this system. All right, you ready for the next, guys? They're the Babylonians.
Is it easier? Oh.
I mean, there's only two symbols. There are two symbols. I know you want to tell me that's an upside down triangle, but triangles don't really have direction. It's just a triangle, isn't it? And I'm going to call the next symbol an arrow, you know, like on an arrowhead, just so that I have something to give it a name for. There's no names assigned to these like there are in the Egyptians. There's only two symbols. The first one, the triangle, has a value of 1. And the arrow has a value of 10. And I really do hope you look at that and say, okay, what about big numbers? Right? Like that seems like there's not enough there. So they accomplish the big number issue slightly differently. They have a place value system. You see, the Egyptians didn't have a place value system. Their numerals themselves had place value associated with them, right? So like when I drew a scroll, you knew how much the scroll was worth, and the number of scrolls told you how many were in that place value. But there really wasn't a place value need because of the size that each symbol represented a size of something. So their symbols do represent sizes, but they aren't very big. They're 1s and 10s. So instead they have a place value system. We have a place value system as well, right? So a 3 in the 4th place over means something different than a 3 in the 10th place over, right? The 3s don't mean the same thing depending on where they're located in our numbers. The same thing's true for them. They have a place value system, but they don't have a place value system that's powers of 10. They have a place value system that's powers of 60. So the first place on the far right, just like ours, is the 1s place. We would have the 10s place next. They have the 60s place next. We'd have 10 squared. They would have 60 squared. And I'll draw one more just for the sake of having done so. If we continued, we'd have 60 cubed, 60 to the 4th, 60 to the 5th, and so on. Okay, pretty good so far. Okay, powers of 60. Okay, so we're going to see how this works in their numerals. But we're still looking, again, like we did last time, at what comes before, what comes after. So comes before, we take away a 1, a triangle. Comes after, we add a triangle. So let's see how that looks when we have this numeral.
I see.
First of all, it's really long, right? But do you see that I have those triangles on the end that I was just talking about? Okay? Those are each value 1. So no matter what this digit or what this whole thing represents, that's not the question right now. The question is simply, how do I find the number that comes before? How do I find the number that comes after? And it's all about adding or taking away one of these triangles. So on this one, the easy question to answer is the one that comes before, because all I got to do is take away a triangle. How many triangles are there?
9.
There are 9. So everything that came first, which is, and I don't fill mine in when I draw them. You don't need to as well if you would like. I just draw open, empty, okay? I have a triangle followed by 5 arrows, I think, and I also leave those hollow. This is just a time's sake thing because I don't want you guys to spend forever shading stuff in, all right? And then I would have 8 triangles at the end. Okay, everybody good with that? I just take away a triangle. That's how I get the number that comes before. What, however, will I have to do if I add another triangle on? How many triangles will I get? 10.
So
But a 10 triangle, say that louder, Danielle.
just add an arrow.
The 10 triangles would be equivalent to an arrow, right? So this is like what happens when you get 10 pennies in your pocket, right? You want to carry 10 pennies in your pocket. You'd much rather carry a dime. Agreed? Same thing here. So I'm going to take my 10 triangles and I'm going to make it an arrow. So how many arrows will that give me? 6. How much is 6 arrows worth? 60. Okay, but they have a base 60 system, correct? So we don't keep 6 of this particular item because it's worth 60, and we trade it up again for another value, and it'll become 2 triangles. So the value after the one that we have is simply 2 triangles. Does anybody see a problem with that? It looks like a 2, right? So in our system, what we would do is we'd have a spot here where we'd put like a 0, right? We have a placeholder, kind of like Annika mentioned earlier with the Babylonians, it's sort of, or not Babylonians, Egyptians. They have this natural built-in placeholder 0 business going on. The Babylonians don't have that. So I imagine bookkeeping was not so nice. Because when you tell somebody that they owe you this much money, they very well may give you, in essence, $2 and not $120, which is what this is equivalent to. Okay, so let's take a look. We're going to talk, we're going to write some of those things down here in a second, but actually part C says, how else could the value in B be interpreted? Well, this actually could be interpreted as the number 2. But what we're really meant for it to be interpreted as was the number 2 in the 60s place, right? It's 2 60s, which is 120. So this is what it should be, because we know more about what's going on in the problem. But if you were just given that numeral, you wouldn't know that, right? You wouldn't know. And then it says, what is this value? Again, when it talks about this value in all my problems, I'm talking about the original problem I started with. So back up here at the beginning, what was it originally? What was this thing? So let me show you how you decide where place values change, because this is a really important feature that everybody gets confused on. So these are all worth 1, right? And the next pieces are all worth 10s, okay? So the bigger value always comes in front of the smaller one. That's always how it works. So everything that I've currently highlighted is in the 1s place, because the bigger value, the 10s, comes before the smaller value, the 1s. So what that means is that this point right here, I have a break, and this is the 60s place. So the 60s place and have the 1s place. And we can count. How many 60s do I have? I have 1. So literally I have 160. Like 1 times 60. And then how many 1s do I have? I didn't say that very well. I have 9 1s here, but what do I have here?
5 10.
5 10s. So I have 5 10s and 9 1s. So what value is in the 1s place? 59. That's actually what I meant to ask. What value is in the 1s place? Well, I have 5 of these 10 things, so that's 50, and then I have 9 of the 1s, so it's 59 that's in the 1s place. So I really have 60 plus 59, which is 119. And that's also why you can recognize that this right here was supposed to be giving me the number 120. That's the number that's supposed to be coming after. But there's not a very good way of writing it down. So what are some pros and cons of this system? Somebody tell me a pro. Start with a pro. I'll let you do that con in a minute, though.
Simple. Just
2 symbols. The 2 symbols is fantastic. Don't you agree?
Yeah.
It is easy to draw. You guys can all draw arrows and triangles. Even if even if I made you shade them in, you'd be okay. Simple to draw. Anything else that makes this an easy system?
It just goes by increments of 1 and 10.
You only have to remember 1s and 10s. That's also something that is kind of different than any of the other systems we're going to encounter. It's similar to the Mayans. We'll get there. But, yeah. So, Emma told me something she doesn't like is that it's confusing. It's confusing. Obviously, not error, but the issue that we're seeing happen in Part C is a big problem, isn't it?
Yeah.
Really is. And not only that, but there's actually one more thing that it could represent. This number could be, hang on. Oh my goodness, come on. This could be the 60s place, and this could be the ones place. So this number also would look the same as if it were 61. Right? You can get away with that one a little bit better because you could say, well, we'll just space them apart a little bit and then it'll be all better. And you could kind of get away with that a little bit. You can't get around the fact that two of them together actually could still be 120 or 2. But, you know, how far spaced apart does it have to be for you to really believe there's a space there? That's a little bit hazy as well. Yeah, so what's happening here that's causing problems? There's a couple of things. Number one is that there's no 0 placeholder. All right, I don't have the ability to put a 0 at the end and call it good. There's also not ways, like if I did want to write 61, they would still look like the two triangles. And I mean, like maybe I could put some space in between them, but there's really no way to distinguish when the symbols repeat, right? So when I repeat symbols that are next to each other. So like I told you over here, that the bigger number comes before the smaller one. But what if there weren't any bigger ones? What if this really was the number 160 and 9 ones? There's no bigger number that comes before the smaller one for me to draw that red line. I don't have a red line possibility very easily. And so it runs into some problems with that too. All right, so let's take a look at what happens in turning one of our values into one of theirs, because this is very different. So we have said that this is the base 60 system, right? Powers of 60. And so we have to actually figure out what happens when we have powers of 60. Well, I know that I've got the ones place, and then I've got the 60s place, right? I need to know what is 60 squared. So somebody grab your calculator for me, or do it in your head, or whatever you want to do. It's 3,600. Good. I'm running out of space already. And what is 60 cubed, the next place? It is a big number. 216,000. And I'm going to stop right there. And the reason I'm going to stop right there is because the number we're dealing with is already smaller than any of those, well, than the final number I just wrote down, right? 216,000. So here's the way that this works. Whichever of these values is the biggest one that will go into what I have is where we start. So we're going to start with 3,600. And we're going to divide 43,205 by 3,600. And I'm happy for you to use your calculator to do that. It sounds like Valerie already did that for me, and she gets 12. Actually, I want to show it to you in a different way, though. Draw this line here, because this will make it a lot more concise. We're going to use this method. The answer, 12, is on the right-hand side. So somebody tell me, what is 12 times 3,600? 43,200. Man, it's awfully close, isn't it? Okay, so if I subtract, what is my remainder? 5. For the sake of what we're going to do next, like later on in the lesson, I don't even think we'll get to it today, but eventually, we want to use the next place value whether it works or not. So I recognize that 60 does not go into 5, but we're going to put a 60 here and we're going to put a 0 and we're just going to do the steps anyway. I know there's no justification for why it matters right now, but just trust me for later, okay? Okay, got a 0 over there. And then my last place value is a ones place, right? So I divide by the number 1. And when I divide by the number 1, it goes in 5 times 5 times 1 is 5. So I stop when I get both a 0 when I get a 0 after having divided by 1. That's when I stop all the division process. When I get a 0 after dividing by 1. A 0 remainder. Okay, so here's what we do. We take the 12 and we say, how do I write a 12 in Babylonian? So you tell me, how do I write a 12 in Babylonian? Arrow and 2 triangles. And then I go to the next one, which most of the time will not be a 0, but ours is. A 0. How to write a 0 in Babylonian? You don't. They don't have a 0, unfortunately. So we're just skipping beyond it. We'll have opportunities later where we will write zeros. And then our last value is a 5. How do I write a 5 in Babylonian? 5 triangles. And even if you separate them, kind of like I did with spaces, there's still no way to confirm that this is the ones place and this is the 60 squareds place, right? There's nothing you can do to designate it. The space potentially might tell you that one's in the ones place and maybe the next one's in the 60s, but there's no way to designate that there's a 60s place missing. This is simply the best you can do. It's a limitation of the system. So that's what you got. You've got an arrow and 2 triangles, and then maybe you put a space in, or maybe you don't. I don't even know that it much matters for my sake. And then you have 5 triangles. Oh, the Mayans. The Mayans. You know, we're 7 years past the time that the world was supposed to end, right? 2012. The Mayans said the world was going to end. Yeah, I didn't even see the movie. I don't know about that, but I just know that that was the thing. So like my grandfather, he lived through the 2000, right? Year 2000, Y2K. The world was going to end. He was certain of it. Yeah. He was sure his car was going to stop working. It's fascinating stuff. Oh yeah, all sorts of interesting things. All right. Mayans. The Mayans are very interesting. They have only 3 numerals. So that's kind of cool. Much like with the Babylonians, few symbols. That dot has the value 1. The horizontal line has the value 5. And that shell has the value 0. 0. They usually call it a clamshell when you see it written in resources. It's a clamshell. Can you imagine it, right? The clamshell that goes like this? My terrible drawings. Looks like bread. I could buy that. Pie looks so good. Kind of looks like a smiley face, to be honest, right now for me. So, all right. They have a very interesting system. They've got the 1s, 5s, and 0s. It is a place value system, much like we have the place value system base 10. The Babylonians have the place value system base 60. Their place value system is a modified base 20 system. Okay, so let's talk about what base 20 system would mean, and then we'll talk about how they modify it. So base 20 system would mean that we have the 1s place, the 20s place, the 20 squared, the 20 cubed. That's what it would look like, okay? All powers of 20. But in their system, they have the 1s place, and then they have the 20s place. And then when they get to the 3rd place, they don't do 20 squared, they do 20 times 18. And then after that, they do 20 squared times 18. And then they do 20 cubed times 18. So they do powers of 20, but there's this weird 18 inserted in the middle there. Okay? Well, I'll show you a little bit more in a minute, but that's what they have. It is actually written vertically. So jot this down. I'm not going to write it on my screen, but you should definitely write it in your notes. The smallest place is on the bottom. The biggest place is on the top. Right? So for us, the smallest place is on the right. The biggest place is on the left. Well, their smallest place value is on the bottom, biggest place value on the top. And they always write their dots above their bars in a place value system. So for instance, if you wanted the number 6, it would be a horizontal line, the bar, with a dot on top. You wouldn't put the dot below. You'd put the dot on top of the bar. Okay, so let me write down what I said before in their system. They basically have the 1s place. These are place value holders. They're not meant to sort of designate the vertical bars. This is the 20s place. And then I have 18 times 20. And then I have 18 times 20 squared. And I'd have 18, times 20 cubed, and so on. So let's actually figure out, either in your head or on your calculator, what is 18 times 20 right here? Do you know what that is? 360 is right. Good job, Emma. 360. Why do you think that they were so concerned to have the number 360 as a part of what's going on as opposed to having something else. 360 has to do with circles, but there's a reason for that as well. Had to do with the sun. The Mayans were all about the sun. So what's something that you know of that's almost 360? Days in a year. There's a little bit of error there, we recognize, yes. It's approximately the days in the year. That's why this 360 shows up. It's special, right? It's kind of like for us as, Christians, when you hear the number 7, there's something special about the number 7, right? When you hear the number 144, if you've read anything in Revelation, there's something special about the number 144. There's something special about the number 12. For them, with the sun, there was something very special about the number 360. So it was incorporated into a lot of the things that they did and the way they structured their society. Okay? So that's why that's showing up in there. Okay, so let's take a look. Just like with the other systems, if we're looking for the numbers before and after, we're taking away or adding a ones value. And the ones value here is represented by which symbol? A dot. So it's all about adding or subtracting a dot to the place value on the bottom, because the bottom is the lowest place value. So here's the number we're going to take a look at. We have 2 dots and then a bar, and then 4 dots and then a bar. And we will change this into our system later, but that's not the point at the moment. The point at the moment is to figure out what number comes before and what number comes after. So right now, my red line that I just drew shows you that whatever's below that red line is the first place value. This is the ones place, and this is the 20s place. And you might ask, how do you know? Why did you notice to draw the line there? Well, look back over here at point number 4. It says within the same place value, the dots are written above the bars. So over here, when my dots that are below my red line changed to bars above it, the place value had to change, because dots are always written above bars. Okay? So if I want the number that comes before this, what would I need to do to make that happen? We're going to either be adding or taking away a dot at the bottom. If we're doing the number that comes before, what would I do? Take away. All right, so this value on the top stays the same. It doesn't change. None of that is affected. But the value on bottom has a dot removed. Take away a dot, take away one value. By the same token, add a dot to get the value to go up. But what happens when I add a dot here? I get 5 dots, but I don't write 5 dots because there's another way to write the number 5. You write it as a line. Okay, so the 2 dots and the bar didn't change, but now the value underneath it has 2 lines. And we've encountered a problem. What problem have we encountered? Well, C asks us, how else could we interpret the value that we just found in part B? What number could this represent? The easiest value it could have represented is 17. Why could this represent the number 17? Yeah, each line's 5, right? 5, 10, 15. 2 bars or 2 dots is 2 more, so that's 17. This could represent the number 17. It's not supposed to, right? I mean, we didn't mean for that to happen, but there's not a good way to give indication otherwise. I mean, there's already space between the bars. It's not even like with the Babylonians where I can just sort of pull them apart a little bit. There's already space there, right? So this could be represented as the number 17. Or, heaven forbid, and I have people who do this sometimes, they just want to make each one of them their own. So they say, oh, look, there's a 5 in the ones place, and there's a 5 in the 20s place, and there's a 5 in the 360s place, And there are 2 in the, and 360 times 20 would be 7,200ths place. They're just going to make each piece its own place value, which it could be, right? I mean, nothing to say it couldn't have been this way. I don't know what that adds up to. Oh, yeah, I do have this one written down. 16,305. 16,305 would be written exactly like 17. Obviously not good. So, what was the original value? When we began the problem over here, what was our original value? Well, I've got the ones place and I've got the 20s place, right? So how many are in the ones place here? Can you count it up for me? More? 9. There's 9 down here in the bottom half of my pink box. There's a line that's 5, 4 dots. How many is above the red line in the second place value?
7.
That one's 7. So what I actually have in this problem given to me is 7 20s and 9 1s. So I have 7 times 20 plus 9 times 1, because it's the 20s place and it's the 1s place. So which is 149.
Is that the only way to interpret it?
No, there's lots of ways to interpret it. So as a default, we need to all talk about it in the same way, right? So we need to figure out when we're working in class, what do you expect? What do I need from you so that we do know that we're actually talking about the same value? So we will only change place value when we have to. So when I looked over here and I said I drew that red line there, that red line absolutely had to be drawn. There was no choice on that matter. In theory, could I have drawn more red lines to separate place values? Well, yeah, I could have. So our default as a class is going to be that we only draw those red lines to change place value when we absolutely have to. Okay? So when we look at this number, we're going to draw as few place value breaks as we have to draw. Here, there was one place value that had to be drawn in. Anything else would have been sort of like, well, maybe there's a place value break somewhere else too. And we're going to say we're not interpreting maybes. We're going to assume that there's few digits as possible. Okay? So, that said, let's take a look at what happens when we try to convert back into from our system back into their system and draw those pictures. So we did this with the Babylonians, took a large number. And when we did this, what we had to do is we had to know how much each place value was worth. So I wrote down that we had the ones place, we had the 20s place, and then we had the 360s, right? 20, I'll write it actually out, the 18 times 20, which was 360. The next one is 18 times 20 squared. I already did this before, I mentioned it as 7,200. We'll go one bigger. What is 18 times 20 cubed? Mm-hmm, 144,000. And I actually know that that's more than I need because my number is only 58,000. So we're going to look at dividing by every value smaller than the one that we actually have. And I call this a division algorithm. So we start with our 58,532. And we divide it by the biggest thing that will actually go into it, 7,200. Yep. So how many times will 7,200 go into 58,532? 8. And then what is 8 times 7,200?
57,000.
Okay. And then we subtract. So what do we get when we subtract here? You guys are welcome to grab calculators. 932 is correct. Okay, so what am I going to divide by next? 360. How many times will 360 go into 932? Almost 3.
It's like 2 times.
It'll be 2. Yeah. And then what's 2 times 360? 720. Yep. Okay, so 932 minus 720 is what? Yeah, 212. There we go.
20 will go into that 10 times.
Yep, so now we're down to 20, and 20 will go into that 10 times. So 10 times 20 would be
Yeah, that would be 20.
200, right? Subtract to 12, and divide by a 1, and 1 will go into 12 times. So again, do you notice I stop when I get the 1 with a remainder of 0. I will always get a 1 division at the end with a remainder of 0 before I stop. And these numbers over here on the right-hand side tell me exactly what I need to draw out by place value. And the very nice thing is it's actually written vertically the way it needs to be drawn too. The 8 at the top means I need to draw 8 at the top, and then I need to draw the 2 that follow it, and then the 10 that follow it, and the 12 that follow it. So 8 at the top. How do I write an 8 in this system?
A line and then 3 dots above it.
Oh, good. So the line with 3 dots, and the 3 dots go on top of the line. The next one is a 2. How do I draw a 2 in this system?
2 dots.
2 dots. I'm just going to space it out for now, and then I'll push it all together. How do I draw a 10 in this system?
2 lines.
2 lines. And how do I draw a 12?
2 2 lines with 2 dots on top of it.
2 lines and 2 dots. Okay, so this is the correct representation, but you do run into a problem on this particular one as well. That's why I picked some of these, right? Because I want you to see the problems.
You think that yeah, I see.
Doesn't it look like there's 12s at the end?
Oh, yeah.
It does, and there's really not a good way to distinguish between. Now, there is something that's very interesting about this system. We didn't have an example to show it, but it actually does have an advantage over the Babylonians. The advantage that it has is it does have a 0.
Yeah.
So if, for some reason, when I did my division, I actually ended up in a 0 inside this red box, I'd have a way to do that. It draws a shell in to represent that placeholder, and that's definitely an advantage. Didn't have it on this particular problem, but it's an advantage. So some pluses and some minuses. Hopefully you've seen them as we've gone through. We still have ambiguity, right? What do I mean? What about when I have those dots and lines? How do I know where the place values actually break apart? A plus sign, or a positive. I do have zeros, very few symbols.
And it's also fun.
It's also fun. One of the nice things about this is that with my dots and my lines, I don't have, I feel like it's not as messy,
Yeah.
right? I mean, like the triangles and the all those symbols that we had from the Egyptians. I mean, like all those things are more concentrated on making them neatly drawn and that kind of thing. I don't have to worry about that as much on this. That's kind of a nice fact.
Easier to grasp than the Babylonian one.
The Babylonian one had a base 60, and I think base 20 is easier than base 60, even if it is a modified base 20.
It's easier to figure out.
Yeah.
It's easier to figure out. So you look at it and you're like, I can piece it out a little bit easier than the other one, for sure. All right, so you have no official homework, but here I have a unofficial homework for you to do the next time. It's very simple. All I need you to do is, with your phone, I would like for you to take a picture of the clock on top of Rayleigh Chapel.
Okay.
All you need to do, bring yourself a picture of the clock on top of Rayleigh Chapel next time.
Do you want to print it out?
Nope, I don't want to print it out. You can have it on your phone. Okay, so just snap a shot when you're walking by there at some point in the next couple of days, and I will see you here on Wednesday.